Okay, the last trend we're going to talk about is ionization energy, and I want to make sure that you have a good understanding of what it means. It is the energy necessary to remove the first electron from an atom. So first ionization energy, first electron. And what happens is you have an electron, you give it energy, and if you remember Bohr's model of the atom, they jump to higher energy levels. Well, if you give it enough energy, it can jump completely off to the infinity area. And that amount of energy necessary to push it to the highest energy level off the atom is called ionization energy. And it's a function of how close that electron is to the nucleus, because that's an attractive force and you have to overcome that, as well as how positive the charge is in the nucleus. So there's two things that affect it. It's very closely related to atomic radius. So if there's enough energy to overcome the attraction of the protons in the nucleus to the electron can be stripped off the atom. And the energy necessary to remove the first valence electron is called ionization energy. So it decreases from top to bottom within a family. That's because the electron becomes further and further. The atomic radius increases. It takes less energy to remove that electron because the protons are so far away. Okay. And shielding effect also contributes to lower ionization energy because it increases the atomic radius. Okay, that's Coulomb's law. So if I'm looking at lithium, 1s2, 2s1, I have 3 protons in the nucleus, and I've got one lousy little electron here. Cesium has 55 protons, so it has a huge number of protons, but we're talking xenon 6s1. So that last valence electron is way out here. And even though there are way more protons than there are in lithium, that electron hardly even knows they're there because there's 54 core electrons between it and the nucleus. It doesn't even see the positive charge, so that one's real easy to remove. Very low ionization energy. Compared to this one, which is relatively close, it has a higher ionization energy. Okay, going left to right across the period, the ionization energy increases because the electrons are closer to the nucleus, that's the atomic radius decreasing, and the effective nuclear charge increases. The increased stability is due to the arrangement of the electrons in the orbitals. This has 3 protons, 1s2, 2s1, 10 protons, 1s2, 2s2, 2p6. So you got your protons, energy level 2. That electron can be pulled off. Here you have your protons, energy level 2, but there are 8 electrons out here. Okay, each one of them feels a net or a effective nuclear charge of 8 plus, because there are 10 protons subtracting the 2 core electrons. And so it's very hard to remove those electrons, and they have a smaller radius because of their increased effective nuclear charge. The effective nuclear charge here is 3 minus 2. It's only 1. Okay, and so it's much easier to remove that electron than it is in neon. It also has to do with the fact that this is a completely filled orbital. But what is the overwhelming reason why is because of those effective nuclear charge and the radius, not because of the stability. So if you notice, ionization energy increases across a row, left to right. But if within a family, oops, not a straight line, within a family, it goes down. Or within a family, lithium, sodium, it goes down. Okay, because the electron gets further and further away. Now this is where it gets difficult. Multiple ionization energies are what happens if you start taking off more than the first electron. So second ionization energy, you remove the second valence electron, meaning it's already lost the first one. It's a positive 1 ion. You're now taking off the second one. Third ionization energy means you're taking off the third one. It's already lost the 2. You're pulling it off. The third electron is already coming off something that has a positive 2 charge. And they keep going like that. Okay. one thing you should notice, and I'll show you on the next chart, is that for successive ionization energies, the value goes up every time. Because every time, now you're taking off an additional electron is being removed from a positive ion. Okay, they attract each other. And you're trying to take another one off, it gets harder and harder every time. Okay, so this chart should be in your notes. Okay, I don't expect you to memorize the number, but I do want you to look at it. This is the first electron being removed. So this right here is a neutral atom. Same number of protons and electrons. And every time you take off another electron, the numbers go up a lot. Okay, and within the first column, you would notice that argon is the highest because it has the smallest radius of the neutral atoms. And so this is following the trend that I talked about earlier, the first ionization energy trend. But what I want you to do is go through, and even though argon has the highest first ionization energy, I want you to go through and circle which element has the highest second, third, fourth, fifth, sixth in its column. So within this column, sodium has the highest value. Even though argon was highest before, argon's still higher. It just isn't as high as sodium is. And then IE3, IE4, IE5, IE6, and IE7. Okay, even though every time argon goes up, it's initially is the largest value, but then it's not the largest value anymore, or the next, or the next, or the next, or the next, or even close on the end. Okay, and I want to talk about why the one that is got the highest IE under multiple columns has to change every time. Okay. So largest value in each column on the chart. Why is the IE4 for aluminum greater than any other element in period 3? So I'm going to go back. We're just going to look at aluminum. So for aluminum, it has the largest value of IE3 of anything else in its group, in its family. Sorry, IE4 in its family. And that's because aluminum is neon 3s2 3p1. So after losing the first electron, it becomes neon 3s2. After losing the second electron, it is neon 3s1. After losing this electron, it is now neon. And now I'm trying to pull an electron off of neon. Because having lost the first three, it loses all its valence electrons. It's got a positive 3 charge. And you're pulling an electron out of a noble gas configuration. And that's what's true about all of those. Okay, so the charge on aluminum just before the fourth electron is moved is positive 3. At that ion, so if we're talking Al3+, it is neon. And that has 13 protons because it's aluminum, but a noble gas configuration, which means it is 1 less energy level than before. It's now down to 1s2, 2s2, 2p6. So its radius has gone down a lot. It has 13 protons in the nucleus pulling on those 10 electrons in only 2 energy levels. So what you have is you have a effective nuclear charge of 13 protons minus 2 core electrons, which means it's an 11 effective nuclear charge. That's huge. Makes the radius very small, makes that attractive force between the protons and the electrons very high, which is why it has the highest IE4, because now you're trying to take away one of these guys. Okay, and that's true for all of them. So to identify which element in period 2 would have the highest IE3, period 2 means we're looking at anywhere from lithium up to neon. Okay, the highest IE3 means you are pulling an additional electron from an ion with a positive 2 charge. Okay, that means it has a noble gas configuration at a 2+ charge. Well, the noble gas, for example, lithium, is helium 2s1. So if it's a noble gas configuration with a positive 2 charge, that means it's helium 2s2 at neutral. That means we're talking beryllium. Okay, so what I do is identify the noble gas, that's the minimum noble gas, and then I add those 2 electrons to it and I figure out what it is. Okay, so period 3 is anywhere from sodium to argon. IE6 means it has a noble gas configuration at 5+. So the noble gas is neon 3s2 3p3. 5+ is phosphorus. And that's how you look at it. Okay, so now using the table of multiple ionization energies, you want to identify element 1 and element 2 from period 2. That means anywhere from lithium to neon. Element 1, if I notice, it's increasing every time, but I see it jumps right here. That's a huge increase, 8 times as much. What that tells me is that element 1, when it has a 3+ charge, is a noble gas configuration. Well, the noble gas is helium 2s2. 2p1 is boron. Element 2 has a jump from 520 to 7298. That's a huge jump. That tells me that element 2, when it's a 1+ charge, is a noble gas. So we're looking at helium 2s1, which is lithium. Okay. Then it says, which neutral element from the chart above would have the smallest radius? Neutral means we're looking here. Okay, would have the smallest radius. Smallest radius means the electrons are closest to the nucleus and take the most energy to remove. So I'm going to look in the first column only for this. The highest energy to remove is element 3. Doesn't mean element 3 is neon. It just means that element 3 of those has the smallest radius because it takes the most energy to remove its first electron. After that, you can't count these guys, okay, because they're not neutral elements anymore at that point.